All right, so as I threatened earlier, I'm going to finish off this discussion of this quasi general purpose finite element code. Okay, we talked about in the last video the input for the model, right? And now I'm going to talk about how we actually go through the steps of writing sort of a general purpose finite element code. Now, it's exactly the same steps that we've taken to solve it that we've used so far. It's just using a couple little tricks to help kind of automate the process. So if you think about what we've done before, is we do step 5 where we assemble the global stiffness matrix. We've done that by executing a sequence of operations in MATLAB, 2 or 3 for each element. We're going to replace that step instead by a loop where we loop over each element in the mesh, compute its stiffness matrix, and put that into the global stiffness matrix. All right. So whether you have 3 elements or 3 million elements, it'll be the same code, just the number of loops it takes. All right. Then we're going to solve it. That's actually pretty much identical to what we've done before. Then we're going to kind of do the post-processing. We're going to write some results, compute reaction forces, and compute the element strains and stresses. And again, to compute the element strains and stresses, we're going to have another loop over each element and compute its strain and then compute its stress, okay? Using the B matrix approach, all right? Okay, so here we go. Here's the end of the input. We've input the files, and now we're going to start the general routine here, okay? So the first thing I'm doing is I'm just defining some basic variables that describe the size of the problems. So these are kind of useful for setting things up. So NN is the number of nodes. I can get that by querying the size of that node coordinate matrix. If you change that up here where it has maybe 3 more nodes, then NN will be changed accordingly here. The number of degrees of freedom, well, there's 2 per node, so it's just 2 times that is the total number of degrees of freedom. That's going to allow me to size the global stiffness matrix as well as the force and the displacement vectors. And also we have the number of elements, okay? So we need that because we're going to loop over elements. And again, we get the number of elements. We can determine that from the dimensions of our our element coordinate, our element connectivity matrix, CON. The number of rows is the number of elements. So this is how you determine the number of rows in a matrix in MATLAB. All right. Now once we do that, we can define the global stiffness matrix as a bunch of zeros and the unknown displacement vectors, again using the number of degrees of freedom. All right, so as we add nodes, this number will change and the size of K and D will change, okay? All right, now we're going to form the global stiffness matrix. That's what's going on here. All right, so this is a loop. E goes from 1 to the total number of elements. So in this problem, the first time it goes into the loop, E is going to have a value of 1, then 2, then 3, then 4, then 5, then 6. Okay, somebody's at my door. I need a sign. I'm going to pause for a second. Excuse me. All right, so I know for you this was no time, but actually that was a bit of a break, so I forget exactly where I was. I think I was describing the element loop, right? So, right, there's 6 elements, so each time it goes to this loop, E will change from 1 to 2 to 3 to 4 to 5 and 6, and that'll allow me to compute, K for the first element, second element, so on, right? So this here is basically just computing the element stiffness, and this bit here is putting it into the correct location into K. All right, so let's talk about that a little bit. Let me actually put a breakpoint here. I'm going to run and execute it right to this point. So we're going through the first time, so you can see E is 1. This is the first element. Oops. Oh, wow. I did. Let's do it again. Step. Okay, so remember, we have this data structure con, right? So each row is the connectivity for that element. So row E tells me the connectivity for element E. So you can see here, if I do con E1, it gives me the first node in element E's connectivity, and the second column, E2, is the second node in that, right? So for this particular one, we're going to have N1 is going to equal 1, and N2 is going to equal 2, all right? So you can see right here, N1 is 1, and is 2. All right, so those are the node numbers for the first and second node in the element. Now we're going to get the X and Y coordinates for those nodes, all right? So X1, Y1 are the coordinates of the first node, X2, Y2 are the coordinates of the second node. So you get that from the nodal coordinate matrix. Again, the row is the node number, so that's why we have N1 or N2 respectively. And the first column is the X coordinate, and the second column is the Y coordinate. So if we step, now you can see the first node is at X equal to 0, Y equal to 0. And the second node is at X equal to 240, Y equal to 0. Okay, so that's the element that goes across, right? Now that I know that, I can basically, once I know the node coordinates, I can compute the element stiffness matrix, right? I can compute the length of the element, right? Here's the Euclidean length. Now I can also compute the angles, the cosine and sine of the angles for this element, right? The cosine of the inclination of the element is the change in x over the length of the element. The sine is the change in y over the length of the element. We need the cosine squared, the sine squared, and the product of the sine and the cosine. So I just define those. So now they're all there, and I just stick them into the element stiffness matrix, right? So for the next element, cosine and sine will change accordingly based upon the coordinates of the nodes of that element, right? So this all goes the same way. In fact, a better thing to do would be actually to write a function from sort of this point on that does the calculation of KE, but I'll show that later on, right? All right, so now I have the stiffness matrix for that particular element. Okay, so now that's the part where I want to describe it a little bit. Now we have to figure out where in the stiffness matrix we're going to put that. So actually, that is done with this array I usually call like the scatter array. And to help explain that a little bit, I got a PowerPoint slide to kind of help with it. But basically, here is 4 rows and 4 columns of the stiffness matrix, right? This is row 1, row 2, row 3, row 4, column 1, 2, 3, 4. They have to scatter into the global stiffness matrix, into some global rows and global columns. That's what this is doing. So this becomes a vector where each entry, the first entry says what global row the first local row should go, what global row should the second global row go, third and fourth, and since it's all symmetric, the column is mapped the same way. So if I get this done correctly, then I can just do the scatter as follows. Okay. So how do we figure out how to get this vector correctly? Well, let's go back and look at this, okay? So I just made a couple of slides. So here's our particular mesh here, right? And we have 4 nodes. Each node has 2 degrees of freedom. So if you look at this table here we have the 4 nodes. Each node has a U and a V degree of freedom. These are what we call the local degrees of freedom, but they correspond to a global degree of freedom, which is basically a row or column in the global stiffness matrix, right? So the X degree of freedom for node 1 goes to 1. That's the global degree of freedom. The Y goes to 2. Then for the second node, 3 and 4. The third node, 5 and 6. And for the fourth node, 7 and 8. So they kind of have this consecutive numbering scheme. Now, so, if we had a 5th node, it would be 9 and 10 and so on and so forth. So actually, if you know the node number, and the local degree of freedom, it's easy to figure out the global degree of freedom it goes to. It's this relationship shown here. So if it's an X global degree of freedom, you take the node number, multiply it by 2, and subtract 1. If it's a Y degree of freedom, it's just 2 times the node number. So like, for example, node 3, its X degree of freedom is 2 times 3 minus 1. So that's 5. Its Y degree of freedom is 2 times 3, 6. And you can play this out for all these and you'll see it works out, okay? So this is a mapping to go from the local degree of freedom for a node to the global degree of freedom node. So if you know the node number and which local degree of freedom you're talking about, you can map that forward to a global degree of freedom with this set of equations. Well, that's what exactly we need to do with this stiffness matrix, if I can find the right. Oops. That's exactly what we need to do here. This is going to be that mapping, all right? And you can see even here, I'll look at, there's 2 times n1 minus 1, and so on and so forth, all right? All right, so how is that going to work? Well, let's look at a simple example. This is element 3. It connects node 2 to node 4. So its stiffness matrix needs to connect the global degrees of freedom for U2 and V2 and U4 and V4. So if you look at this map, you can see obviously U2 and V2 is 3 and 4, and U4 and V4 is 7 and 8. So this scatter vector needs to be 3, 4, 7, 8. So that tells you where the stiffness matrix, the local stiffness matrix, goes into the global stiffness matrix. And that's why you can see I call it a scatter vector, right? It's a scatter vector. All right. And you can check these numbers. Obviously, you can get them by looking up in this table, but if you use these mapping equations from the previous slide, you can see you get the exactly same thing, right? The X degree of freedom for node 2 is 2 times 2, which is 4, minus 1, that's 3. Boom. The Y degree of freedom is 2 times 2, which is 4. There you go. Now for node 4, the X degree of freedom is 2 times 4 minus 1. Right, so that's 7. And then finally, for the Y degree of freedom, it's 2 times 4, which is 8. And that's how it goes, okay? And so maybe what I should do is go through here and actually let's just check the values for the third element. So right now we're at the first element. Let me continue. So now it looped back up to this breakpoint. So now this is the second element. And now if we go further and one more continue, you can see now I've looped up here. So E equals 3. So now I'm at the third element. And now we've defined N1 and N2. So you can see N1 is 2 and N2 is 4. So that's the 2 to 4. That's how this element is connected. I need to get this one so it shows up. All right, now we can get the coordinates using the nodal coordinate matrix. So now we have x1 and y1. So 240 and 0, that's the node 2. And node 4, which is the second node, is 0, 180, right? All right, so now we can compute the length, the cosine, the sine, cosine squared, sine squared, the element stiffness matrix, there it is. But now we need to compute this scatter vector. So you can see this is the global degree of freedom for the X degree of freedom for node 2. 2 times N1 minus 1. So it's going to put in here for N1, 2. So this is going to map to 3, just like we got here, right? This is going to go to 4. This one is going to be 2 times N2. Now N2 is 4, so this is going to be 7 and 8. So if we step over that, you can see that the scatter vector is exactly what it should be. And now we're going to take this 4x4 stiffness matrix and scatter it into the global 8x8. Okay. And there it is. And now if we continue through all the elements until we get out of the element loop, Now you have a fully formed stiffness matrix. That's the fully assembled stiffness matrix with all 6 elements in it, right? All done the same way, but through an element loop, okay? The trick is knowing how to get the global node numbers from the connectivity matrix, how to get the node coordinates from the nodal coordinate matrix, and then to use that mapping to figure out the scattering factor for where the local stiffness matrix goes to the global, okay? All right, the rest of it's pretty straightforward. Now we need to solve. We're going to solve at the reduced degrees of freedom. So you remember up top here, one of the inputs is for you to supply what degrees of freedom are unconstrained, and there they are, right? So this is going to solve the reduced system. So this only works for homogeneous displacement boundary conditions currently, but we can change that. And now we have the displacement, so there it is, okay? So you can see the displacement of node 2 and node 3, right? Now, this is just printing out the displacements, so no big deal there. That's fine. So this just loops over each node and computes and writes out the X and Y displacements. Reaction forces, you know, in the way we've always done it, figure out, multiply the stiffness matrix by the solution, and you get the external forces. But let's go down here and get to where we compute the element strains and stresses. So again, this has to be done on an element by element basis. So we loop over all the elements. It's the same type of loop we did before. But now instead of computing the stiffness matrix, I actually am going to compute the element B matrix, right? So it pretty much goes the same way. All this stuff goes the same way. We need cosine and sine, and that forms the B matrix. All this stuff, N1, N2, here are the coordinates just like the computation of the stiffness matrix. Length, cosine, sine. So that allows me to get the B matrix. And now, instead of using the scatter vector, which is the same as we had before, instead of using the scatter vector to put a local stiffness matrix into a global stiffness matrix, we're using this to extract the degrees of freedom for that element. So this is going to take, you see we use it in D. So this vector is going to allow me to take the appropriate degrees of freedom for the first element or the second element or the third element. So for example, let's get it to be E to be this third element, because that's where our example was. And now if I step through all this stuff, right, here's the B matrix, right? These are the nodes 2 to 4, right? So, oops, dang it. I screwed that up. But, okay, so the scatter vector is the same. So scatter vector is this. So I want to get from the global D rows 3, 4, 7, and 8. Those are the X and Y displacements for the node of this element. So that allows me to get B times the displacements. That gives me the strain. Then I just multiply the strain by Young's modulus, and I get the stress, and I print it out. And so forth, right? This last one, I won't talk too much about this one. This one is just it kind of loops over the elements and it plots each element using some MATLAB stuff and actually scales the deformation so you can see it a little bit. And that is pretty much it. And that is the end of the program, okay? So the important stuff is this, really in here, this element looping, figuring out how you get the node numbers, the node coordinates, and this scatter vector. This is kind of important, okay? All right, so I'm just going to test to make sure that the audio works, and here's my mouse, and this all looks. All right, so this is a video. It will go on YouTube, but this is obviously not intended for general public, but this is specific for some students that are doing a project with me. So I'm going to show you how to quickly define contact pairs in Abaqus in an assembly. So here we have an assembly that's been meshed already. You can see over here we have 6 instances in the assembly: the injector, some nuts, the cap, so on and so forth. So I'm going to show you how to set up a contact pair. In particular, I'm going to do it between the thrust chamber and the injector body. Okay, that part. All right. So when you do the contact, as I mentioned, we define, we're going to do surface to surface contact, not general contact, to save on the iteration time. And I already have in this model. All right, so I'm going to just quickly show you how to define contact pairs in Abaqus CAE. I'm going to do a contact pair between the thrust chamber and the injector, but you'll need to define these for all the parts that are in contact. Again, we'll use the same contact pairs for the thermal contact as well as the mechanical contact. Okay, so here's the model in CAE. Let me just go through the tree a little bit so you get comfortable with how it's organized in CAE. So here we have a lot of different models, and this is from the way I imported in all the various meshes from HyperMesh. But really, it's this thermal model is the one we want to look at. This is the one that I've taken all the parts and assembled them into this assembly. Now, when you look at the thermal model, this tree, we have 6 parts as well as an assembly. So the parts are the individual parts themselves. You see, like if I double click, let's say the injector, here's the mesh for the injector. But we're going to be doing contact, so it's going to be between parts, so we want to operate in the assembly. And you can see I have the 6 instances, which are the 6 parts as I imported them in. And if I click on each one, you can see I basically select those, and you'll see why we need to do that in a little bit when we go to isolate parts to find the contact pair. All right, so the way I usually do this in Abaqus is usually you can see when you set up a model, you have to do several steps. So the various modules allow you to do different operations. So, you know, to define properties, you use the property module. To define loads, you use the load module. Okay, but contact is what's called an interaction, so we'll use the interaction module. You can see each time I select those, the little icons here change. All right. Okay. So this icon here is what allows you to create an interaction, or in this case, a contact pair. And this icon over here is the one that allows you to manage them or look at them or whatever, right? So first we're going to create a contact pair. It'll ask us to select a master contact surface and a slave contact surface. It doesn't matter which is which, but that's what they're referred to due to historical reasons from some older algorithms. But most modern contact algorithms, it really doesn't matter. All right. Now you can see it's going to be difficult to select the contact surfaces in the assembly because they're being blocked by other parts. So one of the things we'll have to do is kind of isolate the surfaces to make it easier to select. This is really probably the one thing you really want to pay close attention to. The defining of the surface is relatively easy. Okay, so first I'm going to create the interaction. All right. Now when I create the interaction, it's going to ask you to give it a name. I highly recommend that you give it a name of the master surface to the slave surface. And again, they're arbitrary, but I'm going to do thrust chamber to injector. You got to give it some name so that we can manage them when you have 10, 20, 30 contact definitions, all right? The type of contact we're going to do is surface to surface contact and use the initial step. Okay, so select surface to surface contact standard if it's not already selected, and then hit continue. All right, now you're not done, right? You can see down here this actually changed, and it's asking us to select the regions for the master surface. Okay, now I want these surface elements, but as I mentioned before, they're difficult to see. So I'm going to just show only the thrust chamber. So the way I do that is under assembly instances in this tree here, select the injector. No, wait, well, okay. Select the thrust chamber. Then you can see that the thrust chamber elements are highlighted. Now, if we go up here, these icons allow you to toggle on and off elements. So what you want to do is actually replace selected. So that will isolate the elements you have selected. So if I click that, you can see now we have just the thrust chamber elements displayed. All right. Now, that's what I want. So we're done with this step of isolating just those elements. So I'm going to hit the X here. This will bring me back to the selection of choosing the master surface. So now I can see all these elements. You can pick them individually. That's a little tedious. The easiest thing to do is to actually pick by angle. And this basically, as long as the elements don't have a angle of greater than 20 degrees between them, it'll view that as one surface. So you can see if I pick the top surface, I get all those elements. All right. So that's pretty good. You know, actually, I could remove some of them here, but I'll show you actually how we do that later on. So that looks good, okay, for now. So I'm going to call that valid for the master surface. So I'm done with picking the master surface, all right? All right, now it's going to want me to pick the slave surface. The problem is that that's on the injector, which I've hidden, so I need to show everything. So click this one here with the odd name, say replace all, but this shows all the elements. And now we just want to isolate the injector. So again, I'm going to go under assembly instances, click on injector, and you can see those elements are highlighted, and then we go back again to replace selected, and now I just see those elements. Okay, all right, so now we have the right elements viewed. So I'm going to close out again this step. This is not the defining the contact step, but this is the step in the step of showing the elements I need to define the surface. Okay, so now you can see we're back to choosing the slave type. Pick surface. Again, by angle is fine. You know, usually I don't create a surface, but you can and give it a name. But usually I just get inundated with a lot of surfaces. But it's fine. You can do that if you want. So here we're going to pick that surface. Okay. That looks pretty good. Although clearly from here, I do not get contact on this capped surface, right? So we can actually get rid of those or unselect just those. If you use the control button, this will allow you to unselect, okay? So if I do control button with angle, it's going to unselect all those. So let's change it from angle back to individual. Hit the control button, and now you see if I select them, it'll unselect various ones. Now that's very slow. The easiest thing to do is to unselect with a window. So again, keep it at individually, control, and then while you hold the control button down, use the left mouse button, and you can draw a select window, and you can see it's turning off or unselecting various elements. Now it's not really essential that you unselect everything on this window, but you know, the more you unselect, the faster the contact search will go. Excuse me with that phone, just let it ring, okay? So that looks pretty good. And so now I'm going to click done. And here it asks you to define the interaction. So for us, I've already defined in this model a contact property. So it's called contact property. So just use that one. That's the most important part. You can select small sliding. That'll make it converge a little faster. And pretty much that should be it. And we'll hit OK there. All right. So that pretty much defined the contact pair surface. And you can see I'll put everything back on again. You can see that they are defined with these little yellow squares, right? And I still have some that I probably don't need on these ears, and also underneath here. So and you know, this might very well happen when you do this, so you can actually go back and edit these. So let's just show you quickly how you can go back and edit this. All right, but maybe I'll stop the video right here because well, it's getting a little long. Okay.